Now the last group, that is your group 18 elements, that is the noble gases. The group 18 consists of helium, neon, argon, krypton, xenon and radon. All these are monoatomic gases and they are chemically unreactive in nature under ordinary conditions. For that reason they are known as inert. They are called as inert gases. Nowadays we call it also as noble gases. Radon is radioactive in nature out of all these noble gases. We can say that. Other gases occurs in very small amount in the atmosphere. For that reason they are also called as rare gases. So see, so many name I am saying you: inert gas, noble gas, rare gases. Got it? Fine. Later on, this when this gas was discovered, later on Mendeleev says that in his periodic table that these elements have got valency 0 and hence it should occupy the 0 group of the periodic table. But after that, when Mosley gave us the periodic table, it came to be in the group 18 of the periodic table. Same 0 group was named as group 18 only because its valency is also same thing 0. We can say that. Clear? So they are neither electropositive nor electronegative, we can say, in nature. These elements are. So the electronic configuration, if you see, it is quite stable. Just now I said you, very stable closed cell configuration it is. It has got except helium, it has got ns2 np6 configuration. Helium has got 1s2, otherwise all other elements have got ns2 np6 configuration. ns2 np6. Due to stable closed cell electronic configuration, these elements possess no tendency to gain or lose electrons. No tendency they have got. That is why they do not take part in chemical reaction. Just now I said you, they are highly unreactive and are devoid of chemical reactivity under ordinary conditions. We can say that. Now coming to some of the properties of the noble gases. All noble gases are colorless, odorless and tasteless. They are monoatomic in nature. Their Cp by Cv values are close to 1.66. Alright, which says that it is monoatomic. These gases are monoatomic. Cp by Cv value gives you what? Gamma. Gamma is equal to Cp by Cv. Gamma is what? Atomicity of a gas. And the value is 1.66, which is nothing but close to 1.66, and hence it is nothing but it says that it is monoatomic in nature. The atomic radii of noble gases are in fact van der Waals radii and are larger than the atomic radii of the corresponding elements of group 17 elements. Got it? And the atomic radii increases on moving down the group from helium to xenon. We can say that. Clear? It increases because atomic radius increases, that the van der Waals radius also increases. Got it? This is due to the increased electronic repulsion between completely filled valence shell in noble gases. As you come down the group, the repulsion increases and hence the atomic radius also increases. We can say that. The melting and boiling points of noble gases are much lower as compared to those of other substances of comparable molecular masses. The melting and boiling points increase regularly on moving down the group. We can say that. Got it? On moving down the group, the melting and boiling points increases regularly. We can say that. The reason is that is in the absence of any unpaired electrons in the valence shells, the atoms or the molecules, whatever we call, of noble gases are held together only by weak van der Waals forces in the liquid state or solid state and can be broken by very small amount of heat. That is why noble gases possess very low melting and boiling point. We can say that. Alright, that is low as, but here what happens is that as the size of the atom increase and moving down the group, the magnitude of van der Waals force increases from helium to radium here. That is why melting and boiling points increase and moving down the group. Got it? Now, noble gases have very high value of ionization enthalpy. The ionization enthalpy of each noble gas atom is the highest in its period. The ionization enthalpy decreases and moving down the group and decreases. That you know it because the atomic size increases. The noble gases are slightly soluble in water. Helium is the least soluble. Helium. The solubility of noble gases in water increases on moving down the group from helium to xenon. We can say that. When you come from helium to xenon, it increases. The solubility of noble gases in water increases. We can say that. Now, next is solubility of noble gas in water is due to dipole-induced dipole interactions. So, when a noble gas is placed in contact with water, the polar water molecules tend to polarize the noble gas atoms. Alright, the last one, which in the van der Waals forces we have studied. The first is your dipole-dipole interaction, Kisam forces. Then second is your dipole induced dipole interaction, that is your London forces. And the third Debye forces, sorry. And the last one is temporary dipole induced dipole interaction, that is your what is nothing but known as London forces or dispersive forces, we can say that. So here that thing happens. The induced dipoles then attach themselves to water dipoles by weak electrostatic forces of attraction. This is why noble gases are soluble in water, although the solubility is not much. Got it? It is not much. So helium, the size is small, so solubility is the least. But if you come down the group, the size increases, so Van der Waals forces increases, so polarity also increases slightly. The dipole-dipole, in dipole-induced dipole interaction, that sort of polarity I am saying. It is not polar. It is not polar. I am mentioning you. Noble gases are not polar, but due to dipole-induced dipole interaction, the polarity temporarily, which is developed. Alright, I said you for that reason, the induced dipoles then attach themselves to the water dipoles of weak electrostatic forces of attraction. Alright, that is why the noble gases are soluble in water, although the solubility is not much. Noble gases are not easily liquefied, however the tendency for liquefaction increases on moving down the group, because the same thing, as you come down the group, the Van der Waals forces that is increases. Got it? And hence what we find is that that is liquefaction also increases, we can say that. Clear? Now after that, how to isolate the noble gases in air? It can be done by that is, isolation of the noble gases can be done by Ramsay-Rallei's method, which you can see it on the screen. The isolation of noble gases in air. The apparatus used by Ramsay and Raleigh for the isolation of noble gases is you can see it on the screen. It consists of a large inverted glass globe of about 50 liter capacity. You can see it there, the glass globe, it is being shown there. 50 liter capacity, fitted with 2 heavy platinum electrodes and 3 tubes. The black one, you can see that is nothing but the platinum electrodes with 3 tubes are there. Yes, you can see it on the screen. If you see minutely, you can get it, all these things. So one for admitting mixture of air and oxygen, second for the entry of caustic soda solution, and third for the exit of the solution. Again I say 3 tubes are there. The first one is for the admitting of a mixture of air and oxygen, the second for the entry of the caustic soda solution, and third for the exit of the solution. A mixture of air and oxygen in the ratio of 9:11 by volume is constantly admitted into the globe, and a discharge of 6000 to 8000 volt is passed. Alright, by the help of transformer, you can see that. Clear, we are having. Under the influence of electric discharge, nitrogen and oxygen combine to form the oxides of nitrogen, we can say that, which are dissolved out in the solution of sodium hydroxide being admitted from the second tube. The supply of air and electric discharge is cut off after some time. Oxygen, if any, is removed by introducing alkaline parallel solution through one of the tubes. The residual gases present in the globe is a mixture of noble gases, which is pumped out, which is being pumped out, we can say that. Clear? So in this way, that is, noble gases is being isolated by Ramsay-Rallei's method, we can say that. The equation are N2 plus O2 gives 2NO, 2NO plus O2 is 2NO2, 2NO2 plus NaOH will give you NaNO2 plus NaNO3 plus water. These are the substances which are being residual substances which are being removed from the third exit. Got it? From the third tube just now which I was talking to you. Got it? And ultimately the gases which are present in the globe is a mixture of noble gases, the residual gases, we can say that. Now this is a chart I have given you, the how to separate the mixture of the rare gases, the noble gases, how to separate it. First, noble gases containing mixture like helium, neon, argon, krypton, xenon brought in contact with coconut charcoal maintained at around 100 degrees centigrade, we can say that. Clear? Minus 100 degrees centigrade, not 100 degree, minus 100 degrees centigrade, that is around 173 Kelvin, we can say that. Because the constituents of the liquid air, if you see, then helium has a boiling point of 4.2, neon 27.1, nitrogen 77.2, argon 87.2, oxygen 90, krypton 119.7, xenon 165. So these are the different boiling point of the different constituents of the liquid air, because we are getting this particular one from the liquid air. Got it? The method which you are getting it, it's a physical method and is mainly employed for the large scale production of nitrogen oxygen from air, and the noble gases are obtained as a byproduct. So we get it, what you can say, the in the chart you can see that first argon, krypton and xenon is adsorbed, and in the charcoal, that is coconut charcoal, and unadsorbed is your helium and neon, which is brought in contact with the charcoal at minus 180 degrees centigrade, 180 degrees centigrade, where neon is adsorbed and neon is evolved, and unadsorbed helium we are getting it. In the next one, that is argon, krypton, xenon, which is adsorbed, it's connected with another coconut charcoal maintained at liquid air temperature. It divides into two. The argon diffuses and adsorbed in the charcoal, in the fresh charcoal, which is further heated when argon is evolved. In the second case, what happens is that the first coconut charcoal, krypton and xenon, is adsorbed in the state, and the temperature is raised to minus 90 degrees centigrade, where krypton is evolved leaving behind xenon, and xenon is further heated in the absorbed state to give you xenon back. So we got argon, we got krypton, we got xenon, we got neon, we got helium, and all the, what you can say, this inert gases is adsorbed. Since the boiling point of the constituents of liquid air are different, they can be separated by fractional evaporation also. The fractional evaporation is carried out in a special type of apparatus called Claude's apparatus. Claude's apparatus, we take it where the fractional evaporation is being carried out. CLAUDE''S. Claude's apparatus, we are taking it. So the physical properties of the noble gases, if you see, they are colorless, odorless gases and exist, I have said you, in the monoatomic state. The Cp by Cv ratio is almost 1.66. They have high ionization enthalpy, their melting and boiling points I've discussed with you, all these things I have told you. The noble gases are only slightly soluble in water, I have told you about it. It's extremely difficult to liquefy the noble gases due to the fact that the atoms are held together only by weak van der Waals forces. Except helium, all other noble gases are adsorbed by coconut charcoal at low temperature. Just now we studied in the what you can say, from the liquid air to separate the mixture of what you can say, noble gases. The extent of adsorption increases with increase in atomic number from helium to radon. Yes, definitely. Noble gases have very low value of enthalpy of fusion and vaporization, we have already studied, which suggests the presence of weak cohesive force even in the solidified and liquefied noble gases, we can say that. Now these are the different compounds of xenon, we can say that, because xenon is a noble gas which forms compound with oxygen and fluorine, we can say that. With oxygen and fluorine, it forms several compounds like XCF2, which is linear, XCF4, which is square planar, XCF6, which is distorted octahedral, XCO3, which is pyramidal, XCOF4, square pyramidal, XCO2F2, trigonal bipyramidal, XCOF2, it is T-shaped, we can say that. These are the different, basically the structure will come in your exams. You will be getting the structures. I have added the structure there. You can see the structure I have added there. You need to practice this particular structure. You need to draw this structure and practice it. You need to remember the name of the shape. So the name of the shape I have given to you. Got it? Clear? So hence you need to remember in this particular manner. Got it? The shape of the molecule, the structure of the molecule. Otherwise, if you ask me the equation is very simple. Like if you want to prepare XCF2, which is linear molecule, we can see in the screen the first one. Then what you have to do is that Xc plus F2, we have to pass the xenon gas and the fluorine gas in the ratio 1:3 in a nickel container at 675 Kelvin. Got it? You will be getting the XCF2 gas. You will be getting it. Got it? Very simple. Similarly, if you are preparing XCF4, the next one, which is square planar, you have to heat xenon and fluorine in the ratio 1:5 in the same thing in a 675 Kelvin at high pressure, that is 6 atmospheric pressure in a nickel container for few hours. You will be getting XCF4 gas, we can say that. So in this way you can prepare these gases, which are this preparation is very simple. It is not at all difficult, we can say that. It is not at all difficult. Similarly XCF6, if you want to prepare Xc plus 3F2 under 500 to 575 Kelvin and under very high pressure, 50 atm pressure, you will be getting XCF6 after some time, we can say, in a nickel container. Got it? So in this way you can prepare the different gases, so to say. Clear? So now this is all about your xenon and this is all about your syllabus. Thank you.